Hello guys, Winston here. I suffer from a mental affliction called being an engineer. It means I go through life looking at everyday objects, breaking them down in my head, wondering how different parts were made, and imagining how they could be improved. It could be anything from cheap plastic knickknacks to consumer electronics to storefront signage. One of the items in my shop that has been a long-standing subject of this silent, sometimes judgmental scrutiny is this, my Ryobi compound miter saw. I bought this thing years ago when I was building out my shop on a budget, and while it does the job I need it to, I've always hated one thing about it. This dust collection system, because to be quite honest, it does absolutely nothing. It's a flimsy funnel that's woefully inadequate for the task it's supposed to do, and it lets dust get everywhere in my shop. That's partly why I made it a priority to install an air filter in my garage, but I know this deficiency can be fixed because improved dust catchers can be had for other miter saws, even if only because of third-party modifications. YouTube channels like Shop Nation and Inspire Woodcraft come to mind. And the idea that I could one day fix my own miter saw has actually been stuck in my head for years now. There's just been one major obstacle. The design constraints for these two-part injection-molded vacuum hose adapter and catcher funnel that Ryobi made revolve around some seriously funky geometry. And while I could try and measure and model and design and iterate against a questionably accurate 3D reconstruction, I've recently gotten a hold of what I believe is a much better option. This is the MetroY Pro 3D scanner, one of Revopoint's latest models, which they were kind enough to provide for me to play with. With this device, if the marketing material is to be believed, I should be able to create a digital clone of my miter saw way faster than I could by painstakingly reverse engineering the thing with calipers. And then from that 3D model, I ought to be able to design an upgraded dust collection apparatus. Now, I've never used a 3D scanner before, so although this is something I'm genuinely excited to try out, please keep in mind that I am not an expert. I'll do my best to provide some basic information about the scanner, how it works, and my experience using it as accurately and honestly as I can. But if after this video you think 3D scanning is something you'd be interested in learning more about, I would highly suggest seeking out a couple other videos about this subject from more experienced people. There's some really solid content out there, both about 3D scanning in general and using specific scanners like the MetroY Pro. I found those quite useful in my own education. With that disclaimer out of the way, let's talk game plan. First, I'll need to scan my miter saw, and probably the dust collection parts too, but separately. Then I'll need to process the point cloud data from my scans into a mesh model that I can import into Fusion 360. In Fusion, I can align that mesh to my coordinate system and start 3D modeling against it. And then with some iteration and 3D printing, I should end up with an improved dust funnel for my miter saw. Conceptually, that all seems very easy, but as a 3D scanning noob starting from zero, there's a few more steps that are implied and probably shouldn't be discounted. First, I need to understand what exactly this device is that I agreed to try out, and also figure out how to use it and the included scanning software that I've never touched before. And for that, I should probably do some test scans on simpler geometry to get the hang of things. Gotta learn to walk before I run, right? So let's dive in, starting with the hardware. This is the MetroY Pro, the latest addition to Revopoint's Metro family of scanners. The Metro series kind of straddles the line between prosumer and professional use cases, and is good for what Revopoint describes as small to medium-sized projects, basically anything up to about 1 meter cubed. The primary method of scanning revolves around using a blue laser source to project patterns on a subject, and using 2 offset image sensors to triangulate where those patterns fall on a surface. The capture resolution is supposedly good enough to register some pretty tiny details, think thread profiles, mold parting lines, or the complicated fillets that injection molding designers love to hide in dark corners of a part. And one of the big headline features of the MetroY line that Revopoint says sets this apart from its predecessor, the Metro X, is wireless scanning. You plug this thing into a power bank, connect your computer to the scanner's Wi-Fi network, and start scanning, which can be handy since you'll often need to point the scanner at your subject from multiple, occasionally awkward angles. Being untethered can be a nice plus. I'm pretty sure you're more interested in seeing how it works though, so rather than hear me read off product details, I'll drop a link to Revopoint's website in the description. They do a much better job explaining how this thing works anyway. Let's go scan something. This is Revopoint's 3D scanning version of Hello World, a little Roman-style bust made of what appears to be plaster. It's the best case scenario for something to scan because it's white and not glossy. That makes it easy for the scanner to get a good laser return on this material. The astute among you might realize that the thing I'm building up to scan is the exact opposite, covered in shiny metal and dark painted surfaces, but don't worry about that right now, that's a problem for later. The Metro line of scanners requires the use of retroreflective dots to serve as reference points. If you're familiar with virtual reality or AR headsets, this is very much like inside-out tracking. A camera in the device looking out finds features in its environment and uses those features to geolocate itself. For inside-out tracking though, I need 4 markers to be visible at any given time. And with an object as small as this mini bust, I can use the included turntable accessory to provide the tracking markers needed as long as the angle I'm scanning at isn't too shallow. Now, I didn't really prepare much for this experience other than watching a couple of YouTube videos. I just wanted to start blasting with lasers. And what I quickly learned is that while the scanning process is pretty simple, the more meticulous you are, the better your results. You need to sweep the light pattern the scanner emits over the surface multiple times from different directions while varying the angle constantly. While you're doing this, the MetroY Pro is continuously snapping stereo images of the subject and sending it to a computer for processing. That doesn't happen on device. The better your computer hardware, the more images per second you can process. After a couple minutes of scanning, I was able to try out the post-processing pipeline in Revo Metro, cleaning up the point cloud and then meshing the data. The software has a pretty linear flow, and I got all the details I cared about from a single scan. No need to fuse multiple scans to create a complete model. So that means I'm ready to scan the miter saw, right? Almost. Scanning something bigger is going to require me to place tracking dots all over the place, because if you remember from earlier, you need at least 4 in view at any given time. When you factor in the MetroY Pro's field of view of just under 50 by 40 degrees, which looks like this, and consider that the optimal scanning range is between 200 to 400 millimeters, or roughly 8 to 16 inches, it works out that you basically need a tracking marker every 4 to 6 inches, and that assumes every tracking marker has a clear line of sight to the scanner at all times. If the geometry you're scanning has a lot of protrusions or irregularities, or you need to scan from many different angles, you're going to need even more to provide consistent coverage. That means potentially dozens of dots per project depending on the geometry's size and complexity. Now, Revopoint included more than enough markers to get me through this project, but I don't like the idea of these being single use. One workaround is to use blocks with markers on them as temporary datums, and Revopoint does have marker blocks you can buy for this purpose, but I was in a bit of a time crunch and I didn't want to wait for a set. Thanks to the power of the internet, specifically the 3D printing community, I was able to make my own reusable magnetic markers in a matter of hours. The key when using these things is that they need to be really stable, otherwise you'll throw off the whole scan. That was a lesson I learned the hard way. I placed these marker blocks all over my miter saw, including sticking some to the saw blade. Now, tracking markers are only half the story. We need to talk about the imaging process too. Shiny objects scatter light, dark objects absorb light. Neither of these things are friendly to optical scanning tools that project a pattern of light onto a surface and interpret the reflected return. My miter saw is not a subject that lends itself well to 3D scanning, at least not without modification. There are products out there you can spray on an object to make surfaces easier for a scanner to read. These will either sublimate in a few hours or require mechanical cleaning to remove. You can also use a DIY mixture of something like alcohol and cornstarch or talc powder in a spray bottle, though they don't always adhere very well to all surfaces. Instead of using one of those options though, I decided to see if I could get by with an all-natural coating of grime and sawdust. There were a few places though where I wanted to make extra sure that the scanner got a solid laser return, so I used some low-tech surface modifiers like tape and paper. My saw's fence was one such area, since that's a set of surfaces I know I'm going to want to reference in Fusion 360. And for the table, since it's flat, I thought I could just place a sheet of paper on the saw as a reference. That ended up working okay, but there was one time I accidentally bumped the paper when I was trying to scan around the saw blade, which ended up moving several tracker markers. The main castings on these Ryobi saws are aluminum, so the magnets in my marker blocks were useless. Because of that bump, I had to terminate the scan early. You can see that once I realized what had happened, I made sure to keep the scanner pointed up to avoid contaminating the point cloud data until I paused and stopped the session. That actually didn't end up being a big deal because one of the things you usually have to do when 3D scanning is to merge multiple sets of incomplete data. You can't always get every angle of a part in one shot, so you can do it in multiple takes. I digitized my saw in 3 passes. Revopoint software can sometimes align and merge multiple scans for you, but on something as complicated and patchy as what I had captured here, setting some manual reference points worked much better. This is the final mesh I got out of the Revo software after doing some cleanup, and all things considered, I'm pretty pleased with it. It's got more detail than I was honestly expecting, especially in challenging areas like the inside of the pivoting arm. If I had more marker blocks and was using scanning spray, maybe I'd try to scan the whole saw, but this right here is more than enough for me to design around. And as an extra point of reference for my design, I also scanned the original injection molded dust collection parts that came with my saw. These pieces are made of black plastic, so scanning them posed some challenges, but since I had no intention of using them again, I figured there would be no harm in spray painting them to a lighter color. These parts, when set on the turntable, ended up scanning into my computer brilliantly without any trouble at all. I brought my completed mesh model into Fusion and aligned it to the global coordinate system as best as I could. I basically just used the edges of my monitor as a reference and lined up the perpendicular edges of the saw against it. After getting my model situated, the first thing I did was draw up a simple test plate to see if it would interface with the real saw. One of the nice things about trying to reverse engineer an international product is that even though the mesh model is imperfect, you can usually assume that an engineer designed it using nice round numbers, or at least to a clean decimal point. That assumption doesn't hold up as well when things are designed in inches. So although my handheld scan of certain dark areas wasn't able to resolve features like M4 threaded holes, that would obviously be asking too much, I can easily make out where the mounting holes and locating bosses for the dust chute are and guesstimate their coordinates with near perfect accuracy. And as evidence of that, my little test piece fit perfectly. With the scan and accuracy of my model verified, I started working on an improved dust funnel. These are the requirements and constraints I had in mind when doing this. 1. The new design must fit the miter saw the same way as the original. 2. It must catch more dust than the original. If it doesn't do this, that's an obvious and instant fail. 3. It needs to promote better airflow and hook up to a vacuum hose with less flow restriction. 4. It can't interfere with sliding crosscuts or miter cuts. 5. It shouldn't prevent cuts through materials up to 3.5 inches thick. That dimension was chosen because 2x4s are the most common thing I'm cutting on this saw. 6. Optionally, we should also be able to perform bevel cuts with minimal disruption, but admittedly this one is the hardest constraint to respect because the clearances get so tight, so we'll just do what we can. My working idea was that I could remake these parts to have a larger cross-section for both better chip collection and higher airflow. Basically, reimagining these parts without the constraints of injection molding and trying to use every last cubic centimeter available within the saw's frame. Early on in the modeling process, I made some helper geometry to aid my design. Stuff like virtual pivot points for joints, and keep-out regions like for where the torsion spring for the saw arm lives, or the fence, or expected stock that I would cut. Now, you'll notice that the keep-out region for the fence here doesn't match the original scanned fence, and that's because I took the shape of the original fence and rotated it plus or minus 45 degrees, then projected that profile onto a flat plane perpendicular to the saw blade. This way, I'll know how close the fence gets to the blade and the dust collection bits during different miter cuts. Also, I made a crude model of the saw's pivoting arm since I can't actually manipulate the mesh model. This gives me a bare minimum working model of the saw that I need to evaluate the various volumetric constraints around the dust funnel. Now, I worked on this model in my spare time on and off over about a 2-week period, and the whole CAD process was way too convoluted to be able to walk you through everything cleanly, but I'll take you through a couple of my thought processes, iterations, and revelations. My original plan for the dust funnel was to draw a bunch of cross-sections that would nestle nicely within the miter saw's mesh model and then loft between them. Now, when you have a complex profile of more than one primitive shape, like the rough profile of my dust funnel, Fusion does a pretty good job of keeping features like hard corners flowing from one sketch profile to the next. But if you're trying to evolve that lofted profile from one general shape to another, and then when you shell a model like that, surfaces get even worse. With follow-on features like fillets or chamfers, one small change can lead to your entire Fusion timeline blowing up in red. Instead of trying to loft one combined mega shape through from start to finish, I learned that things are much cleaner and easier if you loft multiple shapes separately and then combine them at the end. The surfaces are much smoother, and it's easier to control the transition of the loft with rails, and you can make changes to certain parts without breaking everything downstream on a model. This is probably not a revelation for some of you, but I rarely design anything that's not an extruded or revolved feature. This is the final shape of the funnel I ended up with. Compared to the original, it's got a decent amount more capture area down low, closer to where the saw blade is going to be flinging chips outward. For miter cuts, I'm theoretically still within the space allotted to prevent interference, and for normal bevel cuts, there also shouldn't be any issues. As the funnel transitions through the miter saw arm, I squared up the throat near the back where it passes through the saw arm's pivot point. This maximizes the cross-section for flow, utilizing almost all of the space available inside the miter saw's geometry. It then tapers out to a larger port that accepts either a 1 3/4 inch fitting internally or a 2 inch fitting externally. This is in stark contrast to the original vacuum port, which wasn't even 1.5 inches at the OD. To make this model work in real life, I needed to split the funnel into 2 parts, just like the original. And here I needed to consider how I would be producing these parts, which would be on a 3D printer. To make my dust collection upgrade printer friendly, I figured that the plane of the aft mounting flange made the most sense to split my funnel at. This would let me print that haft on a flat surface with minimal support. And the front end of my chip funnel was designed with a flat mouth that was mostly on a single plane, requiring only a little bit of support material. And conveniently, the mounting flanges are at such an angle that they don't need support. To allow the halves of the funnel to interlock just a little bit and hopefully form a tighter seal, I modeled some tapered features along the cut plane so that the funnel side would wedge into the vacuum hose side. The printed parts, even the earliest iterations, fit the Ryobi saw really nicely. The things I improved over time were mostly from design oversights, like making my interlocking features too delicate at first, or failing to consider how there's a part of the saw arm that tapers inward slightly, interfering with my funnel geometry. Of course, it's also something it seems Ryobi engineers overlooked as well, since their funnel appears to also interfere slightly with the saw arm. While I have the OG equipment here though, I think it's time to do some actual testing and get a baseline. Here is a control test with a cut through a 2x4, and you can see the dust funnel is absolutely useless. A ton of sawdust ends up getting blasted into my garage. 240 frames per second isn't quite fast enough to capture individual flecks of dust as they get yeeted by the saw blade, but you can see a bunch of them impinging on the saw's structure when they bounce off and slow down, which illustrates that the general flow of chips thrown off by the saw blade is nowhere near where the dust funnel is. Now, watching this footage over was actually a little discouraging, because I realized that the reason it performed so poorly wasn't for lack of airflow. It was that the chips just never ended up remotely close to where the funnel was in the first place. This didn't bode well for my own design, because other than a slightly bigger mouth and better airflow, it doesn't do anything fundamentally different, but let's try it anyway. Same setup, same cut speed to the best of my ability, and sawdust still ended up everywhere. So it's clear that something different needs to happen in this area. My brain immediately jumped to the idea of making a sort of half-hemispherical ramp to redirect chips up and towards the airflow going into the dust funnel. And to make sure it wouldn't interfere with bevel cuts, not that I've ever made a bevel cut on this saw, this chip amphitheater, as I started calling it, should be easily removable, so I designed it as a 2-part system with magnets. In a later test, I figured out that a ramp that stopped just below my dust funnel still wasn't enough. A big proportion of the sawdust still ended up going over the chip catcher and around either side of the funnel. So I grew that amphitheater, lofting up from a semicircular revolved section to a conic curve. The thought here was that the steeper angles will do a better job of redirecting particles towards the center of the funnel rather than potentially reflecting them back out towards me, which you can see happening sometimes in the test footage. And during the next cut, there were some signs of real improvement. But looking closer, I can still see that there are avenues of chip egress I hadn't considered before, like here at the back of the saw. When the arm pivots down, there's a gap that opens up. I didn't think this was going to be a big deal because, after all, there's a big honking funnel occupying most of the throat here. That ought to capture dust going in this direction, but annoyingly it doesn't. Ryobi engineers, it seemed, had gotten something right when they attached this half-cylindrical cover to the vacuum port side of their dust collection apparatus. But that's just one of the ways that this saw lets dust escape everywhere. The combined internal volume of the saw arm and shroud cavity creates this large turbulent chamber that pushes chips out the front or forces them out the sides around the blade in areas that are immune to the influence of the vacuum's airflow. I would actually go so far as to posit that the design of the Ryobi saw makes dust collection more difficult than it needs to be. Without completely re-architecting the method of dust collection that Ryobi came up with or hooking it up to some ludicrously overpowered dust collector, my minimally informed opinion is that this saw will always leak dust like a sieve. So then, given that perfection seems unattainable without an unacceptable degree of engineering scope creep, where does that leave this project? Is it a success or a failure? Well, I think my benchmark is this. Would I rather use the original Ryobi dust collection apparatus or my own custom design? If we look at the absolute worst case scenario, a sliding bevel cut where I can't use my chip ramp over here, my dust collection system is about as effective as the original, but I never use my saw like this. I'm usually doing simple 90-degree cuts through boards or 2x4s, and in that configuration, the reduction in big pieces of sawdust is maybe 50% or 2/3 over baseline if you squint. But for airborne particulates, that reduction is closer to 80 or 90%. Look at how quickly debris settles and the air clears after a cut. That is a legitimate quality of life improvement. And since there are no real downsides or inconveniences, no regression in the saw's capabilities, I'm definitely keeping these modifications on the saw. Would I like my design to work better? Absolutely. Will this problem continue to gnaw away at my engineer brain for months to come? Almost certainly yes. But are we at the point of diminishing returns? I think so. I don't want to claim it's impossible to come up with a better dust collection system for the Ryobi saw than mine, but I do think that any solution that hopes to achieve substantially better performance will require a radical departure from the style of the original Ryobi equipment. This is all speculation on my part though, I'm not a power tool engineer, but I am really curious to see how others like Shop Nation are going to tackle this problem. If you have a 10-inch Ryobi miter saw that uses the same chassis as mine, which is a TSS 102L, and you want to see if my design will make a difference for you, I'll have the files shared on Patreon or for a couple bucks on my website. The files will include the funnel, the vacuum port, and the adjustable chip catcher with a magnetic base. I designed this part to use 6mm diameter disc magnets, the exact ones I used are linked in the description, and it can be rotated in 15-degree increments for right-handed miter cuts. You just need to add a pause in your slicer before printing so you can embed the magnets. That's all I have for today. I want to thank you all very much for watching, and I also want to thank Revopoint for providing me with their MetroY Pro, which really exceeded my expectations and delivered on its promised capabilities. I've already got a few more project ideas in mind after my first 3D scanning experience. If you're interested in one of Revopoint's scanners, they provided me with a discount link you can use. It'll be in the description below. Anyhow, if you're still here, thanks for sticking around, and I'll be back soon with more CNC projects and DIY nonsense.